we have you're starting?
Yes, sir.
Okay, we have a control system here. It consists of a motor. It's got a tachometer for velocity feedback. And for position sensing, you have this potentiometer. The system is actually here. Here's the motor. This brown item is the potentiometer, and this item is the tachometer. Okay, the signals between the controller and the system are going through this wire. This is an educational system, so all the required signals have been brought out, and there's a panel which describes the system. The system that we are using today consists of a power amplifier, the servo amplifier, and the motor is shown here, and the tachometer is shown here, and the position is shown here. So you can have speed feedback, position feedback. This potentiometer here provides position input. So you can have position output from this potentiometer, position input from this one. Today we're going to run the system open loop. There is no feedback connection. See, so if you wanted feedback, we'd have a wire here. So in open loop, the input to the system is taken at this amplifier and applying a signal, a sine wave signal from this signal generator, which is applied to the input of this system here. Okay. So the sine wave goes in, and this will cause the speed of the motor to change in a sinusoidal fashion. And this will also cause the position to change in a sinusoid, because position being the integral of the speed, if this is a sine wave, this will simply be a cosine wave, so they'll both oscillate. You can see that here. Right now we have set for 0.3 Hertz input. And you can see that the motor is oscillating about 3 cycles per second. So you can see the motor spinning one way when the sine wave is positive, and then stops and goes the other way when the sine wave is negative. You can see the same thing here on the position output, which just oscillates. It should oscillate around 0. 0 is here, but there seems to be some 0 error here, but it's oscillating. So the frequency is controlled by the signal generator. Now I can change the frequency, and you'll see how the oscillation speed changes over here. So that's 0.3 Hertz. So as I increase the frequency, you can see that it will oscillate faster, 0.6 Hertz, 0.9 Hertz. This is a first order system. It has a certain DC gain, and then as frequency increases, the gain will fall. As the frequency increases, the amplitude of the oscillations will get smaller, and ultimately the motor can't keep up with them. So at about 1.8 or 2, I'm at 2 Hertz. At about 3 Hertz, it just stops, can't keep up. So it just becomes smaller and smaller. So let's go back to 0.3 Hertz. The scope shows you the input and output signals. The input signal is taken from the signal generator and is on channel 1 of the scope. The output signal is taken here, at this point here marked velocity, and is on channel 2 of the scope. So now we can look at the scope and see the relationships of input and output. The clear line is the input, and the noisy line is the output. They look about the same size, but they're not. If you zoom in a little bit on the scales, you can see that channel 1 is 100 millivolt per division, channel 2 is 50 millivolt per division. And the frequency can be seen by the time scale, which is shown as 1 second per division. So you can see that there's like about 4 divisions. So right now the frequency is about 0.25 hertz. The input amplitude is 1 division at 100 millivolt, which is 100 millivolt amplitude. The output amplitude is 1 division at 50 millivolt. So this means that the gain is about 1/2. You can also see that there's a small phase difference between the two. We can expand the horizontal scale and measure the phase difference. So you can see here that from this peak of the input to the peak of the output is about 1 division. And since the period is much larger now. Let's see the period. So you can see that the period is roughly 1, 2, 3, 4, 5, 6, 7. About 7 times 500 millisecond, about 3.5. So 7 divisions. So 1 in 7 division is the phase lag. So you would see that the angle is about 1/7 of one full wave, which is 1/7 times 360 or 1/7 times 2 pi radian. If I increase the frequency, there will come a frequency at which the phase lag will be 45 degrees and the output will be 3 dB down. So let's see if we can find that corner frequency. So if I increase the frequency, you'll see that let's focus on the scope. I'm increasing the frequency, the output will get smaller, and the phase lag should increase to about quarter cycle. Let me change this time scale a little bit. Okay, I need to change the scaling on the input too. Okay, so now our new scales is input 200 millivolt per division, output 50 millivolt per division, and time 250 milliseconds. Now you can see that the gain is much less and the separation is about 1/4 cycle. So you can see 1, 2, 3 cycle is the period and about 3/4. 3 divisions is the period and 3/4 division is the phase difference. So at this point I would say the phase difference is a quarter cycle or 90 degrees. Yeah, it's about quarter cycle. So what's the frequency here? The frequency is shown as about 1 hertz. So as frequency changes, this gain, what's the gain? Well, this is at 200 millivolt, that's like 2.5 division. So that's about 500 millivolt peak. The output is about 3 divisions at 50, so 150. So the ratio 150 over 500 that is the gain. And the phase is about quarter cycle or the phase is roughly quarter cycle, almost 90 degrees. So this is the situation, and that's about it. So that's the end.